being here. I'm Burak Toparli and I'm the R&D manager of non-fasteners. So today I would like to give some preliminary results and our work on that we are carrying about conducting on tungsten carbide-cobalt hard metals that we are using in cold forging dies. So just a little fast introduction. So non-fasteners is located in Turkey and we are producing fasteners mainly to the automotive sector, and we are located in Turkey. So and these are the main areas that we are working. So especially every aspects of the fastening and assemblies and the cold forging and particular hard metals. So for the last 3 days we are seeing, and with the previous presentation with additive manufacturing. So today I would like to give you about some information about forging, which is one of the oldest, if not the one of the oldest production methods. So the first evidence goes back to 6000 BC, and with the invention of the fire, then we start using forging more frequently for household appliances and for the weapons as well. So considering the current state of the art for the forging, so it has proven advantages over the other production methods like welding, casting, machining. And the thing is, with forging, it's very suitable for mass production. So if you would like to produce a part with a million of parts, so the forging is one of the best alternative for production of this method. And if you think about the, so if you are a car enthusiast like me, so you often hear about forged connecting rods or forged wheels. This is because when you forge the sample, the mechanical property is higher when you compare this with the casting and the machining because of the continuous grain flow. But still, it is not the perfect, it has some limitations. For example, again, if you consider the current state of the art in engineering world, we are trying to push the limits of every produced part, so the tolerances expected from the parts are increasing. So for cold forging and hot forging, in some applications the tolerances may not be satisfied, so complementary machining is required. And another disadvantage or drawback of this method is that the production technique is that if you have very complex shapes, you have to still need machining to produce part with the forging. So in non-fasteners we are doing some design verifications that we are producing our part with cold forging, but we are separating this operation into two. One of them is that we start with the design verification of the cold forging process. So this is the standard hex bolt. I'm sure you already seen some part of your laboratories or your everyday life, and this is generally a main stage that you obtain to produce bolts with cold forging. So in the first stage, we are doing stage designs. We are looking for the material flows and if there are any imperfections. Then we are getting the forging laws, and this is the first step that we conduct in terms of verification and design studies for cold forging parts. Then we go to die systems, because in the previous case we are defining, or we are using rigid bodies so that we can get the stage design and material flow. But in real world, so we know that the dies are not rigid, so we have to keep an eye on the dies and how they behave in the real world. And this is how we looks like our press. So we have moving parts and stationary parts. And moving part is attached to the crank, and with the moving part is forging the material, so the stage designs and the bolts or whatever you are producing can be produced. So when we look at the main operation where the shaping is taking place, we are using hybrid dies, sorry. So in this case we are using tungsten carbide-cobalt metal ceramic composite materials because of its perfect wear resistance. But since it is, I will talk about in the coming slides, but because of its brittle-like nature, we have to shearing with or press dressing with the tools, with the tool steel, so that I can introduce a press dressing in compression region in the working environment when the die is working on when that tensile loads comes, then this compression can superimpose, and I will be on the, at least try to be on the safe side. because we know brittle materials don't like tensile stresses. And in this case, the designs are carried out, but we have to be sure about our, So the design verification has to be made, because for this particular die, as you can see, we have a die insert here and stress ring, so they are produced differently, and every method, every combination with conventional and non-conventional manufacturing methods are employed. Wire EDM, die sinker EDM, turning, milling, freezing, all kinds of applications are conducted to produce these dies. And after that, grinding, polishing, etc. So we have to be sure that the design is verified and it's performs in the maximum stage. And if the design has a flaw, this also can decrease the OEE, which is overall equipment efficiency. So it is in industry, it's very important, because if your die is failed, then what you have to do is take this out, put the new one, check your setup, and you have to go to quality control so that the sample is okay. Then what you have to do is you are losing time and you are losing money. So we have to be sure that the die design is okay. Thanks to our former colleague Mert Aygen, in his master thesis, he somehow calculated to find a way to calculate hook stresses and radial stresses with this press stressing grains. So by analytical formulations, I can say that I can calculate stresses. So I also have FE modeling, so I can get stresses for tungsten carbide, cobalt, and tool steel for this die, particular hybrid die. But the problem is how to evaluate stress levels against failure, particularly for tungsten carbide, cobalt. Why? I'm coming this topic. So for failure criteria of tool steel H13, we can say that one misses or stress can be applied, because these are well-known failure criteria, and they can be easily calculated from a non-stress state. But for tungsten carbide, cobalt, if you look at this data, the yield stress under tension and the compression is less than unity. So if you compare the yielding occurring or fracturing at like 8,000, I hope you can see, it's 8,000, but in tension it's around 3,000. So there is a significant difference between tension and compression, and von Mises and Tresca can't deal with this difference. And we know that tungsten carbide cobalts are brittle-like nature. I'm saying brittle-like because if it is pure tungsten carbide cobalt, so the tungsten carbide, it is ceramic material, so it should be brittle, but with the addition of significant amount of cobalt, we are introducing some ductility, and this is also required for cold forging dies. And so while looking for the literature for the applications, that which failure criteria that we can apply for tungsten carbide cobalt, and we come up with the more common failure criteria. So this one is takes into account the difference between tension and compression, and it's also preferred particularly in the rock mechanics and granular materials where materials are brittle. So what we did is, so we come up with an idea that we can apply a hybrid failure criteria. So for tool steel we can apply von Mises, and for tungsten carbide cobalt we can apply more color. So there is another issue. So we finally find the failure criteria, but another issue is to find the optimum press stressing ratio for this type of dies. So we come up with an idea that this is the more common criteria, and this green is the current state that current stress rate of the die, and this this one is the outer ring or stress ring, which is we say that we will apply von Mises stress criteria. So what we are doing is we are playing with the press stressing ratio and die insert, so that the difference between this circle and this failure envelope is maximized, so that I will try to be on the safe side. Why? Because I want my tungsten carbide in most compression region, stress level, but there's a limit because then stressing will fail if I put too much compression. So if I increase press stressing ratio above a limit. So I have the failure criteria, and I have the press stressing algorithm that can optimize the press stressing ratio and the outer diameter of the die insert. Then I can go with the trial. So this is a standard hex bolt we are producing, and in the 18 months, 80 dies are produced in order to produce this bolt. And if you look at the average life, it is 140k per life, per die. And this is our current design. And as you can see, there is two stress ring, and this thin layer is also acting as a stressing. So in order to put more pre-stressing on the die. So I have the analytic calculations so that I can calculate the hoop stresses and radial stresses. And from hoop stresses and radial stresses, what I can get is I can obtain more column failure criteria for tungsten carbide-cobalt and one business criteria for the outer ring for tool steel H13. Then I can run my optimization algorithm, and I can find the die insert diameter and the pre-stressing ratio that is keeping my tungsten carbide-cobalt as safe as possible. So this is the current design we already using, and with this new failure criteria and the pre-stressing ratio, we able to simplify the design. And when we compare the performance of these two, the average number of bolts produced per die is 149 for the current design, and 269 for the new design that we come up with, applying more column ratio, more column failure criteria, and with the optimization for the pre-stressing. So it's a significant increase in terms of 81%. And since we also able to decrease the simplicity of the die design, so we can also having a 36% of decrease in the cost. So I increase the performance, I decrease the cost, so I am really happy. So to conclude, we obtain a hybrid failure criteria. We apply the hybrid failure criteria for our dies that we are using in cold forging. And we also produce a new algorithm for pre-stressing optimization. And at the end of the day, we achieved a significant life increase, and on the other hand, with the cost saving, I end up with this application. So when we look at the outlook and the coming work, so up to now I can only try 2 dies, so more dies is required in order to make more reliable conclusions. But when you compare the results, 81% is still significant. So up and down will change. There will be changes in the exact amount, but I'm sure that the improvement will be still there. And the other thing we would like to work on is the tensile properties of tungsten carbide-cobalt, which is very tricky to obtain. So I'm looking for the literature, and the only one available data I can find is from this literature, from this reference. And if you look at the data for the extend grade, the yield property is given as 1500 plus or minus 700. So the standard deviation is high because the intrinsic nature of this kind of material. But in this case, extend is the cobalt content is lower and grains are still smaller than our tungsten carbide-cobalt that we are applying. And we will also conduct a FE modeling because we did in 2D, so we would like to see what's happening in 3D. And we applied column more failure criteria, but also we will look on eye to other failure mechanisms or failure criteria that can be applied to our tungsten carbide-cobalt metal ceramic composite materials. Thank you very much. And I have to acknowledge my company for standing me here and their support for the SSN, the organizing committee. Thank you very much.
Thank you very much for a lecture. Your questions are welcome, please. Do you have any? Yes.
Only a short question. When you showed all the brain stress diagrams, what is about this direction about?
Well, because of the analytic formulas we have in the current hand, We only do it in 2D, and it's planned to be applied in 3D.
Yeah, but is the die, there is a...
So actual direction.
Is it a plane strain situation because the die cannot move?
So there's an actual stresses as well.
Yeah.
So in this case, we considered hoop stress and radial stress because our.
So you said that the actual stress was set to 0 in your.
Well, we will take into account in the coming works.
Thank you once again. And